So with the previous lecture, we have a fairly good idea now as to how a signal can be represented as a series using orthonormal basis functions, and we also saw that a signal can be visualized as a vector, and it can be shown in a signal space. Now we are just one step away from understanding how this method of representing a signal as a series representation will help us in using the Bayesian decision rule for for detecting hypothesis when the hypothesis is represented by signals. So if we quickly recall that block diagram wherein we had a binary hypothesis source, we had the binary hypothesis source, and H1 is the true hypothesis. It was giving out a signal S1t, and H0 it was giving out a signal S0t, S1t and S0t, and just to complete the discussion, in the course of its propagation or transmission, by the time it reaches the receiver in which we have the decision rule, noise gets added. It will be a random process now, a noise for random process gets added, and what we receive at the receiver is a random process, which will be the sum of any of these two depending on which hypothesis was the output of the hypothesis source, and the sum of that and the noise. So now we can write step by step like this. H1 is the true hypothesis. When H1 is the true hypothesis, though the block diagram we have in our minds now, it's a simple block diagram. When H1 is the true hypothesis, the received random process is the sum of S1 of t plus the noise random process, and when H0 is the true hypothesis, we receive this, and keep in mind that the observation interval is this. So this is the duration of S1 and S0, and this is the duration in which the receiver has to observe the signal and take a decision as to whether H1 or H0 was the true hypothesis. The H1 or H0 was the hypothesis, and now we can mention that now this is a process. What it receives is a random process R of t. So a particular realization, that's a sample function, would be, so you can see that I'm using small letter r of t to denote a particular realization, what we call as a sample function. It is like we had a capital letter for the random variable, and the small letter was used for a particular realization of that random variable or a particular value that the random variable takes. So here that this is a random process, and understand that the random process is an ensemble of the various realizations that are possible. Anyhow, these are basics which you are supposed to know. And the sample function, a particular realization, will be, of course, when H1 is the hypothesis, S1 of t plus a particular realization of the noise random process. Similarly, when H0 is the hypothesis, true hypothesis, we realize what is realized, what is received. A sample function, the received sample function can be expressed as S0 t plus the noise sample function. And again, observation interval is 0 to t, which now means that by virtue of the series representation which is possible, we can write the first one as, we can write this as equal to summation k 1 to n can go up to infinity, k is equal to 1 to n, or k phi k t. We discussed this in some detail in the previous lecture, this type of representation. And that will, so this is r of t, the particular realization, the particular function that is received, the realization can be expressed like this. And this will be equal to S1 of t is already we know it can be expressed as a series expansion, series representation. K is equal to 1 to n S1k phi k t. So there is a subscript here to distinguish the two signals. So that subscript I'll borrow, the same subscript I'll borrow. So S1k, k stands for this index, and the first subscript here stands for the subscript which identifies the signals, or the signals corresponding to the hypothesis, plus k equal to 1 to n k phi k t. Now if you compare the coefficients, so if you start comparing the coefficient of phi 1 on the left hand side as well as the right hand side, of course the right hand side can be expressed as S1k plus nk then multiplied by phi kt, a single summation, which is quite obvious, so I will not write it down here. Now if you compare the coefficients of phi k, we note that if we compare the coefficients, we can easily note that Rk is equal to S1k plus nk. That is when H1 is the true hypothesis, and of course k takes on values 1, 2, 3 up to n. So maybe I'll write here k 1, 2, 3, etc. And when H0 is the true hypothesis, by representing this the same way, we will have Rk is equal to, instead of S1k we'll have S0k. So that 0 is for the signal S0 t. 0 stands for the coefficient. So 0 is to identify that the coefficients correspond to this signal. So S0k plus nk, again k 1, 2, 3 and so on. So you can see now that we have been successful in converting the received random process, the received sample realization of the random process into random variables. So whenever H1 is true, now how exactly we perform this in the receiver we'll see later, but it is possible, at least on paper, that when H1 is the hypothesis, output hypothesis from the source, it sends S1 of t, and S1 of t can be expressed, and the receiver receives R of t, and this work shows that, this analysis shows that, or these developments show that it is possible to represent the received sample realization in terms of random variables R1, R2, R3, R4, etc. up to Rn. Similarly, when H0 is a true hypothesis, it sends S0 t as the signal, and it is possible to represent that as again R1, R2, R3 sample, represent them as random variables. So what we have here is again a particular value of the received random process, because we have developed this based on a sample function. Now in general we can write, when H1 is the true hypothesis, the received random variable is Rk, S1k plus the noise random variable, and when H0 is the true hypothesis, Rk is equal to S0k plus the noise random variable, and again for k 1, 2, 3, etc. up to n. Now this means that when H1 is the true hypothesis, again I write here, when this means that when H1 is the true hypothesis, what we receive is not just one random variable. Of course, we have been successful in converting that received random process into a number of random variables, and that number of random variables we put together and we call it as a random vector, a multivariate random variable. So when h1 is the true hypothesis, when h1 is the output, what we receive is r1, r2, etc. up to rn. N can be a large, huge number, which is equal to S11, S12, S13, etc. up to S1n plus N1, N2, N. So what we now we can write it down in a more compact form because we are receiving a number of random variables. So we put it together and we receive a random vector. So we can put it in a more elegant form like this. When h1 is the true hypothesis, the received random vector is equal to the signal vector plus the noise vector. This signal vector is similar to the vector which we were able to show on the signal space in the previous lecture. So you can easily relate it. And correspondingly, when h0, similarly rather, when h0 is the true hypothesis, we receive a random vector like this. But instead of S1, 1, S1, 2 and so on, we will have S01, 02, 03, 0n. And of course noise, random variable, the noise random vector will be there. So again, we can write it in an elegant form like this. So to put it in the final form, when h1 is the true hypothesis, received random vector is equal to S1 plus n. When h0 is the true hypothesis, received random vector is S0 plus n. So you can see that the first example, which is the first block diagram, if you recall, when h1 was the true hypothesis, it was giving out a measurable quantity S1, which I think I used to say it as 5 volt or whatever it is. And similarly, when h0 was the true hypothesis, it used to give another measurable output, which was 0 volt or minus 1 volt, whatever it is. So there we used to have, for h1 true hypothesis, we used to receive a random variable, which will be the sum of that S1 and the noise random variable. And similarly, when h0 is the true hypothesis, we used to receive that value S0 plus the noise random variable. So there we were getting only one random variable, and here we are getting a set of random variables which we'll call as a random vector. The components of the vector are these random variables. So you can see that the previous discussion, the first discussion which we had, which I just now referred to, is a special case of this. This is a more general picture. So this is how we can convert a problem. You can convert the case where we receive signals instead of random variables into a case where we have actually random variables in our hands. Now, with perfect knowledge of the distribution of nk, k is equal to 1 to n, which will be known to the receiver designer or the one who is going to design the decision rule. With perfect knowledge of this, it is possible to get the statistics. But perfect knowledge of the statistics of this, it is possible to get the statistics of this. That means the distribution of this. With perfect knowledge of the distribution of this for k1 to n, it is possible to get the statistical distribution density function of this, which means that it is possible to get the density function of the received random vector, the conditional density function of the received random vector p or h1 or H1, conditional density function of the received random vector when H1 is a true hypothesis. Similarly, one can get, with perfect knowledge of the density function of the noise random vector, anyhow this will be known to us because the signal is known already. Only thing is that doesn't know which of the two signals were transmitted. Since the signal is known, we have these with us. So the conditional density function of the received random vector when H0 is true is also available, can also be arrived at, and we can formulate the likelihood ratio, which now will be a function of the random vector, received random vector, and we can take a decision as earlier by comparing it with the ratio P0 by P1. So you can see now how the receiver is going to work when the hypothesis is represented by signals. Having received the random process, it will receive a sample realization. It has to get these coefficients. It has to get these coefficients, and it has to plug in those values. Now, how exactly it happens in the receiver, we'll see later. It has to plug in those values here in these density functions, which it will have already with it. Then compute this likelihood ratio and compare it with this and take a decision. It is noteworthy that when the receiver detects that H1 is the true hypothesis, and it does that when the likelihood ratio which it computes is more than this. When it detects H1 is the true hypothesis, effectively it is detecting that the signal output is S1 of t, because S1 of t is the output when H1 is the true hypothesis. Similarly, when it detects H0 as the hypothesis, and that happens when the likelihood ratio computed is less than this, it is effectively detecting the signal S0 t, because H0 is represented by S0 t as the output of the hypothesis source. So basically this is the discussion on signal detection. Because I repeat that again, why we call it a signal detection, because whenever the receiver computes this and finds this out to be more than this, it is actually identifying that the hypothesis was H0. Of course, it can make mistakes. We'll see that later, how to quantify that mistake. But if with a well-designed decision rule, the Bayesian decision rule is a well-designed rule, most of the times it will come out with the correct answer. So whenever this is more than this ratio, it is detecting the hypothesis H1, and since H1 is represented by the signal S1t, it is detecting that the binary hypothesis source output signal is S1 of t. So it is detecting the signal actually. We can visualize it as a setup which is going to detect the signal as either S1t or S0t. So with that discussion, we will now proceed, and we will, as I said, now we will quantify the performance of the Bayesian decision rule for signal detection. That is, quantify in the sense, what is the probability of error, how often, or what are the chances that the decision rule, the Bayesian decision rule, can make a mistake. We will discuss that in the remaining part of this lecture, and if it is going to be too lengthy, we will carry it over to the next lecture. So we now discuss the performance evaluation of Bayesian decision rule for signal detection. So basically what we are going to discuss here is what is the probability that the decision rule, the Bayesian decision rule, will make an error in detecting the hypothesis. And as I said earlier, the problem can now be also visualized as one of signal detection. So we are actually trying to find out the probability that the Bayesian decision rule will make an error in detecting the signal, in detecting which of the two signals were transmitted. Now let's first understand that the noise which gets added, if this noise is white, when I say white noise, you know that what I mean is that its autocorrelation is an impulse and power spectral density is flat. So if it is white, then the coefficients nk with which we represent this noise process as a series will be uncorrelated. Further, if nt is Gaussian, if nt is a Gaussian process, then nk will be Gaussian, and when nt is white Gaussian, when nt is white Gaussian, nk will be uncorrelated because it is white and Gaussian because it is Gaussian. And Gaussian random variables which are uncorrelated will also be independent. So that means when nt is white and Gaussian, then nk will be Gaussian and statistically independent. It will be Gaussian and statistically independent. So remember, when the noise which gets added, the noise process which gets added with the signal in the course of its propagation towards the receiver is white and Gaussian, then nk, the coefficient with which we expand nt as a series, will also be Gaussian and statistically independent to each other. And that happens because it is actually uncorrelated if it is white, but since it is Gaussian, it will be independent. Uncorrelated Gaussian random variables will be independent. And now we can call this noise process as additive because it's getting added to the signal. It doesn't get multiplied with the signal. It is getting added with the transmitted signal. So additive white because its power spectral density is flat, or the same thing can be put in other words by saying that its autocorrelation is an impulse, and G Gaussian, additive white Gaussian noise. So here onwards, when we say AWGN, we refer to additive white Gaussian noise, and we are referring to these properties of noise. It is additive, it is white, it's Gaussian distributed, and of course it is noise. So with this in mind, so the summary of this short discussion is that when noise is AWGN, NT is AWGN, NK will be Gaussian and independent. Now with this background we will proceed. Now the first thing that we do is we have the two signals. We are discussing binary hypothesis testing, and we have these two signals. S1t is corresponding to the hypothesis H1, and the other one is corresponding to hypothesis H0, and you can see them as signals representing two different symbols of a binary source. Anyhow, we have these two signals now. Now we have to obtain a suitable series representation for this before we proceed, and that means we should have the required number of basis functions with us so that we could represent these signals faithfully. And the task is now in our hands, in the sense it is now we have to find out the basis function and find a series expansion for this, a faithful series representation of this, and we are free to choose the basis function as long as we are able to represent these two signals faithfully. So what I do is I will outline the process here. That is how I am obtaining the series representation. I will outline it here, and on this side I will show you some familiar steps from linear algebra, or to be more specific, from conventional vector algebra. I will list down some steps here, and I will map those steps onto the signals that we have with us, and through this flow I will show how we are able to express the signals S1t and S2t as series representation. So to begin with, the first step here is, let's say we have two vectors A and B. So remember, this is from conventional linear algebra or the vector algebra, which we are probably more familiar with. And the mapping of this step onto the signals side is that we have S1t and S0t. So let S1t be the signal, S1t correspond to the vector A and S0t correspond to the vector B. And the next step on the signals on the algebra side is that, the vector algebra side is that, the second step is that we divide one of these two vectors with its magnitude. So what happens when we do that is we get a unit vector which I will call as a cap. So when I divide, I get a unit vector. I divide a vector by its magnitude. We'll get the magnitude. We'll get a unit vector, and this we can use as a basis, because you know that a set of bases is nothing but a set of unit vectors, independent unit vectors, and this can be one of the components of that set. So this can be used as a basis vector, and the corresponding step here is that, so we have assigned we call this as A, vector A. So that is, we have mapped this as vector A, this is vector B. We have the two vectors, we have the two signals here, and we are familiar now with the fact that signals can be visualized as vectors. So we divide S1t with its magnitude, and this magnitude, as you know, is obtained like this. So the same thing, we have to take an inner product, a dot product of that signal S1t with itself, and then take put it under the square root. So we do this. This is the inner product when it comes to signals, multiplied by S1 conjugate t dt. And we can readily visualize this as the energy of the signal S1 of t. So we write this as E1, where E1 is the energy of the signal S1 of t. Now this, since the result is unit vector, I am going to get a function. This as a whole will be a function which will be of energy 1, unit energy, and this can become one of our basis, one of the signals, orthonormal signals in our basis set, which means that S1t is equal to root E1 phi 1t, which means that this is S11. So the first subscript here identifies the signal subscript, and the second one identifies the coefficient index. And this means that S1 of t is completely represented as a series representation, with S11 as root E1, S12 will be 0, S13 will be 0, S14 will be 0, and so on and so forth. So we have a partial result here. Now the next step, the third step is that we take this and dot it with a cap. So we have a unit vector already obtained here, which we obtained from this vector A. And remember, we started with two vectors. We obtained a unit vector here, and we now dot the vector B, the second vector that we have, with the unit vector which you obtained here. And what we get is, again, from elementary algebra, vector algebra, you know that what you get will be projection. You will get projection of B. You will get the projection of B on A cap. You get the projection of B on A cap. And now if we do this, okay, let us, before we go to the next step here, let us write the corresponding step here. So the step corresponding to the third step here will be, it will be B is this signal. I have to take an inner product of this and the basis which I got. The basis which I got is phi 1t. I have rewritten it as, earlier if you recall, we had S1 of t by root E1 is phi 1t. So B dot A cap, that is inner product between B and A cap, will be an inner product between S0 t and phi 1t. So when I do that, I get, so inner product among signals is defined like this: S0 t and phi 1t. So phi 1t will be, phi 1 conjugate I have to put here because I am taking an inner product. So S1 conjugate t divided by root E1. Energy root E1 will be real, so we don't have to write a conjugate. So this is actually S0 t into phi 1 conjugate t, which is nothing but the dot product between this and phi 1 t. Now we note that if we do 1 by root of E0 into E1, where E0 is the energy of signal S0 t, integral 0 to t S0 t S1 conjugate t dt, we get what we define as the correlation coefficient rho between the signals S0 and S1t. Now if you compare these two, you see that we can write, so we have S0 t S1 conjugate t root E1. Root E0 is missing, so if I introduce root E0 here, I need to put a root E0 here, and that means I will get this result as nothing but rho into root E0, which you can easily see. If you take this root E0 in the denominator here, you get the rho which we defined just now. So we have this as the result here, and also one can see that this is the same as, in fact, this is the same as 0 to t S0 t phi 1 conjugate t, which means that based on our previous discussion we can write this as S01. We can write it as S01 because we are finding the first coefficient, that is the coefficient of the term with which we multiply phi 1t in its series, in the series representation of S0 t, and the first subscript is for to identify the signals. Okay, and the next step here is that if we do this now, if we do this, that is projection of B on A, which you obtained here, if we multiply it with the unit vector A, we are going to get the component of B along A. We get the component of B along A because you take the projection in a particular onto a particular vector, unit vector, and then multiply that projection with that unit vector, you will get the component of B along A. And the same thing happens here. The corresponding operation here is B dot A, the B dot A cap operation, the result is this, and multiplies with A cap is phi 1 t, so rho E naught phi 1 t will be the component it will be the component of S0t along phi 1 t, component of S0t along phi 1 t. Now the fifth step here is this. We take the vector B, and from that vector we subtract its component along A, and when you subtract from B its component along A, you get a vector. The result of this will be a vector which will be perpendicular to A cap. So when you subtract from B its component along A cap, you will get the result as a vector which is perpendicular to A cap. It is like visualizing the components of a vector. You can verify that by simply dotting this with A cap. You can see what is the result. If you dot this with A cap, you will get vector B dot A cap minus vector B dot A cap, which is 0. So that means when you subtract from B its component along A cap, you are going to get a vector which is perpendicular to A cap. And now the corresponding operation here is from S0 t, you subtract its component along phi 1 t, which was rho root E naught phi 1 t. Now the last step is, so remember on the left side we have the conventional vector algebra, the more familiar vector algebra, and the right side is how we map it onto signals. Now the last step, the sixth step is divide this by its magnitude. So what happens when you divide this by its magnitude? You will get a unit vector, because when you divide a vector with its own magnitude, you will get a unit vector. Also, that unit vector will be perpendicular to A cap, because we have already seen that this is perpendicular to A cap. If you divide it with its magnitude, you will get a unit vector perpendicular to A cap, and hence this forms our second entry into the basis set. The first one was A cap, the second one is this, and you can see that both of these, A cap as well as this, is of unit energy or unit magnitude, and they are orthogonal to each other. So these two are orthonormal to each other. They are orthonormal. So we have the first entry as this, the second entry as this. And the corresponding step on the signal side is S0 t minus rho root E naught phi 1 t divided by the magnitude of the numerator. So how do we get the magnitude of the numerator? We can visualize this as a single vector now, a single signal and we obtain its magnitude. And remember, all these are valid in the interval 0 to t. We need not say, I have been telling that right from the beginning. That is the observation interval. So we take a dot product, an inner product of this with itself, inner product of this with itself, it is dt over there at the edge, and integrate it. That is the inner product of this with itself. That is nothing but an integral of the signal with its of the signal multiplied by its conjugate, and then it put it under the square root. Now this result will be so now here onwards we will concentrate on this. This result will be in that I will concentrate only on the denominator now, and that too what is there within the square root, integral 0 to t s naught t magnitude square, just multiply the terms, minus rho square root of e naught phi 1 t s naught conjugate t minus rho conjugate root e naught s naught t phi 1 conjugate t plus magnitude rho square e naught phi 1 t magnitude square dt. So this is the result of expanding this. And now when we integrate this, the first term, when you integrate, you get E naught, energy of S naught T, and the second term will give minus rho root E naught S01 conjugate, because you have rho root E naught integrate phi 1 t S naught conjugate t. If you had done S naught t phi 1 conjugate t, you would have got S01, which we saw a short while ago. So I'll get S01 conjugate minus rho conjugate root E naught. This will be S01 when you integrate, and finally plus magnitude rho square E naught phi 1 t magnitude square. When you integrate, you will get the result as 1, because it's the energy of phi 1 t. Phi 1 t energy is 1. So we have the result like this, and we observe that we know that S01 we had we obtained S01 a short while ago, and that was rho root E naught. We had it somewhere here. I had explained it, I remember. So S01 is rho E naught. Substitute for S01 conjugate, rho conjugate root E naught, and you will get E naught. And similarly, S01 is rho root E naught. Substitute there, you will get magnitude rho square E naught and the term there, and you can easily see that this is going to get cancelled, and our result will be E naught 1 minus magnitude rho square, and that's going to come under the square root here, because what I have done here is what is there inside the square root. So the result will be E naught 1 minus magnitude rho square under root. Now this will be a signal of unit energy and it will be orthogonal to phi 1t. That means that phi 2t is equal to, this will be the second entry in the set of bases. Just as we had this as the second entry in the set of bases, this will be our second entry. The first entry is phi 1t, which we have already found out to be s1t by square root of its energy. So phi 2t will be equal to s naught t minus rho root E naught phi 1t by square root of E naught 1 minus rho square. And now we can write S naught t is equal to, we can rearrange the terms and write S naught t as equal to rho root E naught phi 1t plus root E naught 1 minus rho square phi 2t, which means that, as I said earlier, this will be S01 and this will be S02. And we already have with us S1t as equal to root E1 phi 1t. So there it goes. We have our series representation now. S1t is root E1 phi 1t. This will be S11 plus, if you want it to be complete, 0 into phi 2t plus 0 into phi 3t. We don't have to bother now what is phi 3t. Phi 3t will be perpendicular or orthogonal to phi 1t as well as phi 2t, and it will be of unit energy. We don't have to bother because S13 is 0. S12 is 0, S13 is 0, S14 is 0, and similarly here S0t is S01 into phi 1t plus S02 into phi 2t. Again S03 is 0. So again phi 3 coefficient is 0, phi 4 coefficient is 0, and so on and so forth. So this is our series. So we have now with us the series representation of the signals. We have the series representation of signals like this. And you can see that if you square this and add with the other coefficient, you will get the energy, which is the square of the energy rather, that is which will be the energy rather, that is the Parseval's identity. And you can square it and add, you will get the energy of S naught t. Okay, so now before I proceed further, I have to, if you have been following this closely, you'll understand that what we have done here is nothing but what I have demonstrated is nothing but what I have demonstrated is the Graham-Smith orthogonalization procedure. Of course, I have not shown all the steps because I have only shown you how to get two bases. The general method you can find in the textbooks, and most of the Indian universities teach this at the undergraduate level, so I will not go into the details. But what I have demonstrated here is the Graham-Smith orthogonalization procedure, and I have obtained the basis functions, and through those basis functions I have obtained the series representation of the signals. Now with this knowledge we will proceed further. So remember that one thing is that the noise n of t, when the noise is AWGN, nk will be Gaussian and statistically independent, and the two signals S1 of t and S2 of t, S0 of t are expressed in the form of a series as I had it now, just now on the board. And now we have, we can write when H1 is the true hypothesis, when H1 is the hypothesis, R1 will be equal to R1, remember R1, R2, R3 like that, we get a random vector. What we receive is a random vector. So R1 will be equal to S11 plus N1, which is nothing but root E1 plus N1. And R2 will be S12 plus N2. Refer to my immediate previous lecture in case you have forgotten this, which will be equal to S12 is 0, so 0 plus N2. R3 will be S13 plus N3, which will be 0 plus N3. So R4 will be N4, R5 will be N5, because you saw that only S11 is non-zero, that is root E1. And when H0 is the hypothesis, H0 is the true hypothesis, R1 will be S01 plus N1, which will be rho root E0 plus N1, which will be rho root E0 plus N1. R2 will be S02 plus N2, which will be square root of E0 1 minus magnitude rho square plus N2. R3 will be S03 plus N3, which will be 0 plus N3. R4 will be S04 plus N4, which will be 0 plus N4. R5 will be 0 plus N5, and so on and so forth. So what we see here is that to take a decision as to, for the receiver, for the decision rule to take a decision as to which of the two hypotheses were true, or to take a decision on which of the two signals were the output, S1 of t or S0 of t, that is equivalent to detecting which of the hypothesis is true, it needs to have, or we need to have access to only R1 and R2, because R3, R4, R5, R6 onwards do not have any of the information on the hypothesis with them. Now what I mean is, if you look at R1 when H1 is true is root E1 plus N1, R1 when H0 is true is rho root E0 plus N1. So the hypothesis information, which hypothesis is true, that information is embedded in this random variable R1. R2, if you see, 0 plus N2 when H1 is true, or root E0 1 minus magnitude rho square plus N2 when H0 is true. So you can see that the information on which of the two hypotheses is true is hidden in this, in R2 as well as this R2. So R1 and R2 are the ones that we really require to arrive at a decision as to whether H1 or H0 is the true hypothesis, or equivalently whether S1 of t or S0 t was the true signal or the signal. If you have R3, you just get the noise term N3. So there is nothing that is in this which is related to the hypothesis. It is just the noise which you get. R3, R4, R5 onwards, even if you have that entire set with you, the infinite values with you, it is of no use, because they don't distinguish between the hypotheses. You just get the noise samples. So you can simply discard it because it's of no use. You cannot, it is no way going to help us in determining in taking a decision as to which of the two hypotheses were true. Of course, one can say with the help of that you can arrive at an information on the noise statistics, but we have assumed that we already know the noise statistics, so we don't have to bother about that as well. So at this point we will end this lecture and we'll continue further in the next lecture.